My name is Kyle Hecker, and this is IQE number 8 for Fluids 307. The first question, the conceptual question is, how is Rayleigh flow defined, and why is it unitless? So the answer to Rayleigh flow is, it is an ideal gas flow with constant specific heat flowing through a constant area duct with heat transfer but negligible friction. This seems like a lot of words and pretty big, but when broken down and thought about it, it actually makes a lot of sense in how it can be true. Then here's the equation for Rayleigh flow, and all of these values, beta is the volumetric dilation coefficient, delta T is temperature, G is gravity, D is distance, V is viscosity, and A is the thermal diffusivity. And when you apply all these units into this equation, it turns out to be unitless. Now, onto the calculation question. So it says, a very strange volcano exploded, and the atmosphere can now be thought of as full of helium. The stagnation pressure and temperature are 1200 kPa and 400 degrees Celsius. This is a very odd blast and killed everyone within a 150-mile radius, as these are very extreme conditions. These conditions are passed through a wind turbine, and this turbine can be thought of as an engineering turbine in order to treat it like an engineering problem, where the outlet stagnation pressure is 1500 kPa. If gamma is 1.667, the CP is 5.14393, and the R is 2.077. If this process can be thought of as an isentropic, what is the power of the turbine per unit mass? And so we start with our knowns: stagnation pressure on the inlet, stagnation pressure on the outlet, and then stagnation temperature on the inlet. Then we're trying to find our power per unit mass, and we're assuming isentropic. And isentropic is reversible and adiabatic, and that will come into play in the second part of this problem. And then a wind turbine acts as an engineering turbine, and we assume steady state. CP, once again, our properties are all repeated, and now we solve. The first equation, we solve for T2 using this little equation here. So when we plug that in, T2 turns out to be 736 Kelvin. Now for the second part of this to find the power, we can use the first law equation, and everything goes to 0 because we're assuming steady state, and we get du goes to 0, and we get mi hi minus mo ho plus w equals 0. Then as steady state, m dot equals mi, and so you just get m, and then you do your equation with delta h, turns into cpt2 minus t1, you divide by m, and you get your final answer after plugging all your numbers in for 326.46 kilojoules per kilogram.